Julian. My name is Christophe Aucourt. Today, Emmanuel Granatello will join me to host this webinar. Both of us are technical marketing engineers based in Germany, focusing on motor driver applications. In this webinar, we will talk about how to estimate power dissipation in motor driver ICs. Designers often need to estimate the junction temperature of a motor driver. Knowing the system junction temperature is an important requirement for safety and reliability. It is usually fairly easy to derive the maximum steady-state chip temperature from simple measurements or calculations. In this webinar, we will review a first-order power dissipation estimation method and see how the numbers can be refined with the help of a simple SPICE test bench. Before diving deeper into the subject, we will briefly refresh our minds on motor driver thermals and power stage basics, covering half-bridge, full-bridge, and three-phase topologies. Let's get started right away and review what a classical motor load current mission profile is. Motor current tend to exhibit a rabbit ear profile. During the T1 phase, the motor spins and the current quickly nears a maximum value. This inrush current relates to the fact that at no or low speed, the motor's back EMF force is very limited. In this case, the current will be limited by the input voltage and the winding DC resistance. The inrush current typically lasts for a few tenths of millisecond. As the motor reaches its cruising speed during the T2 phase, it develops a higher back EMF that will counteract with the input supply. The load current will naturally decrease to establish around the I-load level. This operation can last indefinitely long. Depending on the application, the motor may hit a mechanical stop and stall. As a consequence, the motor speed will near zero, the back EMF will vanish, and the current will rapidly increase, reaching the so-called stall current. The purpose of the motor controller is to detect this current increase and to turn off the motor, thereby ending the T3 period. This is important to avoid the motor and its driver to overheat. In some use cases, the operating cycle may repeat numerous times. Thermal resistance is a quantification of how difficult it is for heat to be conducted and is represented as the quotient of the temperature difference between two given points by the heat flowing between these 2 points. This means that the higher the thermal resistance theta, the more difficult it is for the heat to be conducted. The unit of the thermal resistance is Kelvin per watt or degree C per watt. Although Kelvins and degrees Celsius, are different in their absolute values, they can be treated equivalently in terms of relative temperatures. So what is a thermal design all about? Thermal design is intended to reduce each thermal resistance, described here, so as to reduce the thermal resistance of the heat dissipation path from the chip to the atmosphere. So in a system, we have typically two passes conducting the heat away from the chip. One would go through from the junction through the package into the ambient. Another one would actually travel along the board to end up also in the ambient. Thermal capacitance reflects the amount of heat energy required to increase the die temperature by 1 degree. It is a function of the heat capacity of the material, denoted C, its density, ρ, and its volume, V. A larger package, a larger lead frame, a larger die all contributes to increasing the device thermal capacitance. In motor driver applications, the high power pulse width that can range from a few tenths of milliseconds up to a few seconds, making it necessary to consider the effect of thermal capacitance. When this thermal capacitance is large enough, it can limit the junction temperature to within the ratings of the device, even though the peak power dissipation might be quite large. As power is initially applied, the die is the first component to heat up, storing a portion of the dissipated power as thermal energy. The portion of the power which is not stored in the die will flow to the PCB through the lead frame die attach. The lead frame, with its thermal mass, must absorb a measure of the heat before its temperature rises sufficiently, or better said, before driving the heat into the PCB. This process goes on until the temperatures have reached their steady state values and all of the dissipated power will flow into the ambient air.
So, it is crucial for the motor driver solution designer to have tools that allow an estimation of how the die temperature evolves throughout a mission profile like the one shown earlier. And since mission profiles are very specific to the motor application, the more generic the tool, the better. Simplicity and familiarity with such a tool are also important. And that is why an electrical model equivalent to the thermodynamic behavior has gained popularity in the industry. To derive these models, we could start from finite elements multiphysics simulations or from practical experiment data. Given a power dissipation function, typically a step but not necessarily, the junction temperature dataset can be used to extract the analytical expression of the junction temperature versus the time. This last step can be done with the help of many fitting techniques and tools, under the hypothesis that the thermal system is largely linear. This expression should be a sum of exponentials. Under the same hypothesis, the junction temperature will be the output of a linear thermal system, while the power dissipation will be the input. So the Laplace transform of the junction temperature expression can be found, and this equals to the product of power dissipation and thermal impedances in the Laplace domain. Particular care must be taken for the Laplace transform of the power dissipation stimulus. The thermal impedance in the Laplace domain can be eventually calculated as the ratio of output, that is the junction temperature, the input, that is the power dissipation of the system. This Laplace transfer function is very practical, for example, for synthesizing the thermal impedance as a cascade of resistors and capacitors. A simple and widely used example of RC network modeling of a generic impedance are the Cauer and Foster representation. It is quite interesting that in case of thermal impedance, each RC block often ends up representing the different mediums between the die, where the power dissipation actually happens, and the outside world, where the heat wants to flow in order to re-establish the thermodynamic equilibrium. Thanks to this dualism of power dissipation with electrical current and temperature with voltage, an electrical engineer could easily integrate a very simple thermal model together with an actual electrical model of the motor driver. And this integration can be done in simulation tools like SPICE-based ones. At this point, all that needs to be done in this SPICE simulation is to estimate the power dissipation at simulation time, which means time step by time step, and then feed this value into the equivalent thermodynamic model that is basically the thermal impedance. This will result in a voltage which actually represents the junction temperature.
Depending on the DC motor type we want to drive, there are three basic topologies available to us. A half bridge, shown here on the left, is an inverter composed by a high side and a low side switch. This inverter topology is primarily used to drive unidirectional brushed DC motors. The motor can operate in forward direction by turning on the high side switch, or coast to a stop by turning the bridge output high impedance, or actively brake by turning on the low side switch. An H bridge is composed of two half bridges. The operation is very similar to the half bridge, with the additional feature of being capable of dynamically selecting which motor terminal to be connected to a static supply. This allows a brushed DC motor to run in both directions, forward and reverse. The H-bridge topology is also the basis for stepper motor drive. Last but not least, we have the B6 bridge. This topology is based on multiple half bridges to independently drive the three phases of a BLDC or PMSM motor. A BLDC motor can be energized by turning on the high side device of one leg, turning on the low side device of an adjacent leg, and leaving the third branch high impedance. To spin smoothly the motor, there needs to be a proper commutation table to transition this pattern throughout the different half bridges. Driving a MOSFET requires an understanding of the MOSFET switching waveform. When switch mode operation of the MOSFET is considered, the goal is to switch between the lowest and the highest resistance state of the device in the shortest possible time. The switching performance of the MOSFET transistor is determined by how quickly the voltages can change across its parasitic capacitor. Two of these capacitors, the CGS and the CGD capacitor, correspond to the actual geometry of the device, while the CDS capacitor is the capacitance of the base collector diode of the parasitic bipolar transistor, so-called body diode. To gain a better understanding of the fundamental procedure, we will neglect the parasitic inductances present in this circuit. In the first step, the input capacitance of the device is charged from 0 to the threshold voltage, named VTH. During this interval, most of the gate current is charging the CGS capacitor. Only a small current is flowing through the CGD capacitor. As the voltage increases at the gate terminal, the CGD capacitor voltage has to be slightly reduced. This period is called the turn-on delay, because both the drain current and the drain voltage of the device remain unchanged. Once the gate is charged to the threshold, the MOSFET is ready to carry current. In the second interval, the gate is rising from the threshold voltage to the Miller plateau level. This is the linear operation of the device when current is proportional to the gate source voltage. On the gate side, current is flowing into the CGS and CGD capacitor just like in the first time interval, and the VGS voltage is increasing. On the output side of the device, the drain current is increasing, while the drain to source voltage stays at the output voltage level. Until all the current is transferred into the MOSFET and the diode turned off completely, the drain voltage must stay at the output voltage level. Entering into the third period of the turn-on procedure, the gate is already charged at a sufficient voltage, the Miller plateau, to carry the entire load current, and the rectifier diode is turned off. That now allows the drain voltage to fall. While the drain voltage falls across the device, the gate to source voltage stays steady. This is the Miller region. All the gate current available from the driver is diverted to discharge the CGD capacitor to facilitate the rapid voltage change across the drain source terminal. The last step of the turn-on procedure is to fully enhance the conducting channel of the MOSFET by applying a higher gate drive voltage. The final amplitude of the VGS determines the ultimate on resistance of the device. In the force interval, VGS is increased from the Miller plateau to its final value around about 10 volt in this example. This is accomplished by charging the CGS and the CGD capacitors. The gate current is now split between these two components. While these two capacitors are being charged, the drain current is still constant, and the drain to source voltage is slightly decreasing as the on resistance of the device is being reduced. The turn-off procedure for the MOSFET transistor is basically backtracking the turn-on steps. This starts with VGS being equal to the gate driver supply, and the current in the device is the full load current. A turn-off delay is required to discharge the MOSFET input capacitors from its initial value to the Miller plateau level. Once the drain to source voltage has been slewed, the gate voltage resumes falling from the Miller plateau to the threshold voltage. The MOSFET is in its linear operation, and the declining gate to source voltage causes the current in the drain to decrease towards zero. Meanwhile, the drain voltage is steady at the output voltage level, and the rectifier diode is forward biased. The last step of the turn-off procedure is to fully discharge the input capacitor of the MOSFET. VGS is eventually reduced to zero. In general, a half-bridge is a rather simple circuit containing two switching elements with the load connected at the output. The two switching elements can be turned on and off independently with some obvious restriction. The load either being positive, in other words, current flowing out of the half-bridge, or negative, current flowing into the half-bridge output. This corresponds respectively to the cases of a motor acting as a load on the left, or as a motor acting as a generator on the right. The basic operating mode of a half-bridge is fairly simple. The top side MOSFET is turned on, and the left lead of the motor is connected to the power supply, while the right lead is connected to ground. Current starts flowing through the motor, which energizes it, and let's say it turns in forward direction, and the motor shaft starts spinning. A constant frequency PWM signal can be used to modulate the speed of the motor by adapting the ratio between on and off time. In a half-bridge, you should never close both high side and low side MOSFET at the same time. If you did that, you just had created a really low resistance path between power and ground, effectively shorting out the power supply. This condition is called shoot-through and is an almost guaranteed way to quickly destroy your bridge or something else in your circuit. To avoid shoot-through, we need to insert dead times. One between the low side MOSFET turning off and the high side MOSFET turning on, and another one between the high side MOSFET turning off and the low side MOSFET turning on. During that time operation, the motor current is carried by the body diode of the rectifier. In case the bridge is sourcing current, it is the low side MOSFET that will act as a rectifier, and the output voltage will temporarily go one diode drop below ground. This operating mode is usually called low side recirculation. Similarly, when the bridge is sinking current, it is the high side MOSFET that will act as a rectifier, and the output voltage will temporarily go a diode drop above the supply. This operating mode is called high side recirculation. EMI noise in the frequency range of 150 kHz to 30 MHz is primarily comprised of the switching frequency and its harmonics. This type of noise can be reduced by using EMI filters. However, for the frequency range of 30 to 300 MHz, which includes the FM radio band, EMI filters are less effective. In this frequency band, minimizing the parasitic capacitance on the switch node and controlling the motor phase voltage dV/dt are critical to reduce conducted emissions on the motor lines. The higher rate of change in the voltage on the motor lines, the more difficult it becomes to meet conducted EMI compliance. As we can observe here, the magnitude of the spurious noise is directly proportional to the input supply. The first frequency roll-off is influenced by the PWM signal duty cycle, while the second frequency roll-off relates more to the rise and fall time of the signal. The lower the F2 frequency, the lower the created spurious noise in the FM band and above will be. Depending on how fast the motor phase voltage transition, the frequency F2 can range from hundreds of kilohertz to a few megahertz. Half bridges losses break up into three types: switching losses, conduction losses, backgate diode losses. In a simplified model of a switch mode operation, a MOSFET is either fully on or fully off. However, a more realistic model must acknowledge that the transition between the two states isn't instantaneous. MOSFETs have a finite switching time. The MOSFET operates briefly in the high power dissipation linear mode every time it switches. MOSFET switching losses are a function of the motor current, the power supply, and the switching frequency. As we learned before, the drain source current starts to flow as the gate source voltage reaches the MOSFET threshold voltage, while the drain to source voltage transitions later on as we slew through the Miller plateau. The switching losses are maximum for a short period of time as drain source voltage and currents are both high. Conduction loss is the power dissipated when current flows through the non-zero resistance of a MOSFET channel. The drain to source resistance of a fully enhanced MOSFET is denoted RDSM. Conduction losses are simple I²R losses when the MOSFET channel conducts. The average conduction losses are calculated using RMS current instead of instantaneous current, thus becoming a function of the operating duty cycle. The rectifier MOSFET has also backgate diode losses. During the dead time, the body diode carries the motor current. The switch itself has no backgate diode losses as the diode doesn't conduct any current.
One other way to estimate power dissipation is with the help of electrical circuit simulators, such as SPICE-based ones. MOSFET manufacturers usually share publicly the SPICE models of their devices, and sometimes they are found in different levels of complexity. The more complex the model, the heavier the simulation will usually be. So it is crucial to choose the right level of complexity for the right purpose if one wants to minimize convergence problems and execution time. In the case of this MOSFET, we found that a level 0 model would be a good compromise between complexity and the purpose of estimating power losses. Level 0 from this manufacturer, however, does not include thermal effects, or at least these thermal effects cannot be computed at simulation time. Level 1 does this job since the model has an input for the junction temperature. However, it also includes a very complex modeling of the electrical parasitics at the expenses of long simulations and very demanding convergent problem solving. Eventually, we have settled on the level 0, and here we can see how in QSPICE the simulated RDS on fits with the datasheet values. We could also appreciate how also the modeling of the dynamic behavior at level 0 is quite good compared with the datasheet specs. Indeed, we have extracted the gate source charge in a QSPICE test bench by ramping up the gate source voltage while integrating the gate current up to 10 volts, as specified in the datasheet. And the same thing can be done for the output charge by integrating this time the output current while the drain source voltage ramps up to 50 volt and while the gate source voltage is kept at 0, which again are the conditions specified in the datasheet. In addition to the vendor's SPICE level 0 model, we wanted to propose also a further approach. In practice, we have attempted to create our own MOSFET SPICE model, including the effects that are the most relevant to the power dissipation estimations. One main driver for the creation of this model was the need to determine the operating region during the operation. Indeed, the operating region tells us how to separate the channel losses into conduction and switching losses. That's because when the MOSFET operates in the linear region, we assign the dissipation to the so-called conduction losses. When it is instead in saturation or pinch-off region, we know that the current is transitioning from 0 to the load current, the behavior indeed associated to the definition of switching losses. Another advantage is that the diode and the channel currents can be measured separately, allowing for the calculation of the body diode losses. From the theory, a MOSFET is generally and successfully modeled as a voltage-controlled current source, a variable transconductance, which represents the channel conductivity. In parallel to this, there is a diode representing this body diode. The channel transconductance parameter, here we call it Kp, is a function of the technology, the physical property of the MOSFETs, and includes the temperature dependence of the MOSFET resistivity. Inverting the theoretical expressions, the Kp parameter can be extracted by identifying some key quantities from the vendor's datasheet, which are the RDS on, the VGS drive voltage and current at which the RDS on is defined, and the threshold VGS voltage. If the internal drain and source resistances are known, the model can be further refined. The parasitic capacitance can also be added externally and can be modeled as complex as needed. Regarding the body diode, we opted for a very simple and practical ideal diode model, which is available in the QSpice native library. In practice, this has a piecewise characteristics where the breakdown, the off, and the on regions are associated to a resistive linear behavior, and these regions are connected by a quadratic law. These diode model parameters can be extracted and refined, relying on the data available in the datasheet. In our case, we use the diode characteristic graphs. One missing point of this approach is that the reverse recovery charge of the body diode cannot be modeled, or at least is not modeled. However, motor drivers usually work at PWM frequencies that are in the order of few tens of kilohertz. And in these circumstances, the QRR effects are generally negligible. Last but not least, we have enhanced this model, including also the effect of the junction temperature on the body diode forward voltage, on the MOSFET transconductance, and on the conduction threshold voltage. This QSpice simulation test bench has been developed with the focus of determining the power dissipation in the high and low side MOSFETs for a half-bridge configuration. This could be, for example, the case of a pump or a cooling fan. The time transient simulation outputs a dataset of currents and voltages of the circuits, and the power dissipation can be calculated at simulation time step by time step, by multiplying currents with voltages using behavioral sources. These behavioral voltage sources will then output power data over time, which can be post-processed via the QSpice measurement statements in order to determine average powers within an integer number of PWM cycles. One consideration must be made about the drivers. We have developed a driver model that almost ideally controls the slew rate of the switching node. In a few words, these drivers pump and drain the exact gate current needed for the MOSFETs to ramp up and down the switching node at a constant slope. In this way, we can superimpose a desired slew rate or a list of slew rates in case of stepped simulations, and all this without worrying about setting up the driver with the right strength for each step. The consequence of this approach is that the capacitances and the gate charges are almost irrelevant for the MOSFET losses estimation, since the trajectory of the operating point during the switching events will be determined by the controlling drivers. Also, one could notice that this approach is almost equivalent to the power losses first-order calculation method that we have shown before, because both are based on the hypothesis that the switching node commutes linearly. We have also included an estimation of the PCB traces resistance, which we have aligned with the values measured on the PCB that we used for comparing all these estimation methods. An effort has been made to make sure that the DC settled value of the load current is regulated regardless of the power dissipation and regardless of the duty cycle. This is done by controlling the load resistance with a very low bandwidth feedback regulation loop. And this load current is a modeled effect of what could be the motor torque, together with a typical DC motor inductance. Let's compare now how the test bench differs between the level 0 model from the vendor and our simple FET model. For the vendor's level 0 model MOSFET, only the total power dissipation of each FET can be calculated because there is no access to the body diode current information. Also, conduction and switching losses cannot be separated because we don't have the exact operating region of the MOSFET. However, this level 0 model is quite straightforward to set up because one can simply import the vendor's SPICE model in QSPICE and recall this model via the QSPICE MOSFET symbol. The simple MOSFET test bench seems instead more complicated at a first glance. This is due to the fact that we need to add measurements that allow the separation of the power dissipation contribution. The body diode current is taken separately from the channel current, and the capacitance, even if largely irrelevant for the reasons explained before, have been included anyway for the sake of completeness, and in order to cross-check the gate driver behavior versus the level 0 vendor's model test bench. One can notice also the presence of the operating region and the junction temperature nodes for each MOSFET. Ultimately, a thermal behavior of the package has been included to determine the FET's junction temperatures increase due to the power dissipation estimations which are made at simulation runtime. The measurement statement's complexity also is visibly increased in order to allow for the calculation of the different contributions to the power dissipation. Here we can appreciate the power estimations that comes out of the two test benches for a forced junction temperature of 25 degrees C and with a stepped load current. On the left side are the results for the vendor's model test bench after post-processing the time transient simulation data. Here, all we can show are the total losses for the high side, for the low side MOSFETs separately. On the right side, the simple MOSFET model allows us to have a deeper look at what happens to the different losses contributions. For example, we can see that because of the direction of the current exiting the switching node in this example, the high side FET body diode carries no losses. The result is different for the low side body diode, of course, which instead is the one carrying the load current during the dead time. We can also observe how at currents above 5 amps, the conduction losses become predominant and grow with a quadratic law, while switching losses grow linearly. Also, the conduction losses are almost equally shared between high side and low side FETs because of the 50% duty cycle. By comparing the two plots, the left and the right, we can conclude that at the same junction temperature, there is a difference of 5% in the total losses. Considering the variability that a MOSFET could exhibit over the production, this error is acceptable. In order to appreciate the quality of the estimation methods we just mentioned, we have built an experimental test bench using our MPQ 1922 half-bridge pre-driver. In this setup, we have measured the input power and the output power after the switching node. Under the hypothesis that the AC component of voltages and currents is negligible, the average power in a PWM cycle can be successfully approximated to the product of average currents and average voltages. To confirm this hypothesis, we have also compared these average measurements done with digital multimeters with the average power computation done on actual currents and voltage measurements done on an oscilloscope. With a thermal camera, in the meantime, we have kept under observation the junction temperature, taking care to record the results only when the system has reached its steady state. The difference between input and output power equals to the total power dissipation in the two MOSFETs and in the PCB traces. This data point has been recorded under different load conditions, giving us the benchmark datasets that we need. And this table summarizes the power dissipation calculations, the simulations, and the measurements results. The first thing that immediately captures the attention is the reassuring fact that in case of low-side recirculation, it is safe to not consider body diode losses in the high-side FET, and to not consider switching losses in the low-side FET. This hypothesis was carried out in the first-order approximation calculations and is confirmed by the FET SPICE simulations. It is also interesting to notice that the body diode losses in the recirculating MOSFET could be greatly miscalculated at high current ratings. Indeed, the simple FET model includes temperature effects of the forward diode voltage. This effect consists of a reduction of the diode forward voltage with increasing junction temperature. But at the same time, in the same MOSFET, the RDS on in the channel increases with increasing junction temperature. This phenomena, if exasperated, could bring to the point that the RDS voltage drop could approach the body diode forward threshold. That means that the body diode could start conducting even outside of that time, in parallel to the RDS on of the recirculating MOSFET. This situation is equivalent to reducing the RDS on by allowing an alternative path to the current flow. And the net result is that the losses in the recirculating MOSFET actually decrease. However, this behavior is not desirable, since the body diode is generally not designed to carry currents for an extended period of time. In summary, it is worth to notice that this effect could be observed using a simulation model with a more or less accurate temperature dependence, while it is totally neglected in the first-order approximation calculations and in the level 0 SPICE model. The effect of the PCB traces should not be left out of these computations and simulations, at least when dealing with high currents. Our trace resistance measurements on the board have indeed identified a total of circa 20 milliohms shared between input, ground, and output paths. In the case of 8 amp load current, the traces could concur with a whopping 1 watt losses. That is circa 10% of the total power dissipation. To be noted that also copper has its own thermal effect, with an increase of resistance with increasing temperature. This effect is more complex to model, though, as one should be able to extract the thermal characteristics of the PCB. So we have left out this effect together with the reverse recovery of the body diode and other approximations mentioned so far. Eventually, we found out that because of these approximations altogether, the simple MOSFET model results deviate from our experimental results by circa 7.5%. And this happens at relatively high currents. That means it happens at relatively high temperatures. The level 0 vendors model is also quite reliable at low currents, but as soon as the thermal effects become important, its power estimations are too optimistic and too far from the reality. The first order approximation is surprisingly not far from the simple MOSFET test bench results. In our case, we have also included in the RDS on its increase with higher currents based on an educated guess and approximation of the junction temperature at the different current levels. This, plus the approximation of the body diode behavior, results in an overestimation of the losses at high currents that kind of compensates the lack of losses computation in the PCP, at least for this case. The first order approximation, in conclusion, remains a good, quick method to evaluate at a glance if a MOSFET could service a specific application.
We are now reaching the end of this webinar. Let's review a few points we discussed to help us in our motor driver power estimation. First, we should remember that first-order approximation, even though they may not be perfect, are simple and a pretty good way to estimate 80–90% correctly the losses. For those of you who are familiar with electrical simulators such as QSpice, we showed a simple test bench to accurately estimate and break down the MOSFET losses with an even better degree of accuracy. This method is quite helpful to find a reasonable trade-off between motor driver power dissipation and EMC compliance. Finally, the largest source of inaccuracy we could identify between first-order estimation and/or simulations is the MOSFET RDS(on) junction temperature dependency. As the device is heating up, its channel resistance is increasing, thereby pushing the losses further up. Thank you so much for your attention. Emmanuel and I are now open for questions.
Thanks a lot, Christoph and Emmanuel. Great presentation. So I want to remind everyone that you can mouse over the bottom of your Zoom webinar interface and you will see the Q&A button. Please type in any questions that you might have. We are waiting now for more questions to come in. I want to remind you that we are recording the session and we will send you a link in the next days. With the link, you will be able to watch today's webinar on demand. We will also send you a link to the PDF presentation. Please also check our MPS webpage and webinar schedule to see additional sessions. So let's get started with the first question. And it is, how fast would you typically drive the power stage FETs in a motor driver application?
Well, that's an interesting question because that probably largely depends on the applications you're looking into. We have quite a bit of experience, for example, with people dealing with motor driver in the automotive body segment, where the EMC compliance, conducted EMC levels, as defined in the IEC standard, can be quite stringent, and the motor that may be located some distance away. You know, some people, they may do this so-called mechatronic system. Everything is very compact. They can have a tendency to be more aggressive, switch faster, reduce the power dissipation. Other people may have the motor 0.5 meter, 1 meter, 2 meters, 3 meters distant from the control unit. And we have seen people in these cases that may have an interest in going as slow as microseconds, several microseconds of rise and fall times, where when things are very compact and especially when motor power might be quite high, we may see people being as aggressive down to the hundreds of nanosecond range.
Okay, thanks a lot. The next one is, which thermal model do you use, Cower or Foster? What is the difference?
Well, actually, it doesn't matter which you use, but I find personally more practical and more significative of, let's say, the physical construction of a MOSFET or of an IC in general, the Foster method. Because you can see how here between every junction there is an RC in parallel, and if every junction between each one of these blocks represents the junction between two pieces of metal, or the junction between the die and the die attach, and the lead frame, well, you can say very quickly, okay, this RC block represents the thermal resistance of that medium, which can be the die, which can be a metal, which can be the die attach. So let's say if one has done an experiment on an existing package, on an existing device, one can really understand how much each, let's say, each part of the device under test contributes to the thermal impedance, and could also identify that how much the PCB, which eventually is what is in the power of the electrical designer, how much the PCB influences the total thermal impedance and thermal resistance. I hope that answers the question.
Thanks a lot, Emanuel. The next one would be, these methods describe power dissipation in DC motors, but how can they be applied to three-phase BLDC motors, where the current profiles in each phase are different and are sinusoidal with lower frequency than the PWM?
Can you repeat the question? Sorry, Julian. I missed
These
some.
methods describe power dissipation in DC motors,
Yep.
but how can they be applied to three-phase BLDC motors, where the current profiles in each phase are different and are sinusoidal with lower frequency than PWM?
That's a good question. So the load profile is different. I mean, at the end of the day, what are we talking about? Depends on the waveform of the load current. So can be sinusoidal or quasi-sinusoidal, and depending on the waveform, one has to consider its RMS value. And yeah, I think that's the way. Or when doing manual calculations, or when you have a simulation dance bench like this one, instead of having a constant load, one can simply emulate the current levels, the waveforms themselves, and most importantly, the power dissipation has to be integrated over a electrical rotation period. Let's call it like that, which will be the period of the current waveform. So of course the simulation can become a bit, I don't know, a bit longer depending on what is the frequency at which the motor rotates and at which you want to calculate the power dissipations. But I would do it that way in the simulator.
Okay, thanks a lot. Next one is, in H-bridge, high side recirculation or low side recirculation, which is preferred?
Oh, that's I don't think there is really I don't think there is really any preference. I think at the end of the day, what may dictate a choice for a system level integrator are actually the capabilities of the motor driver that he is working with. Because not every motor driver has the built-in infrastructure for doing current sensing on the high side or on the low side. So depending on the architecture of the motor driver and how it is capable of sensing the current, I think that would probably be the most influencing parameter on selecting high side versus low side recirculation.
Yeah.
Okay, thanks a lot to both of you. The next one is why low side MOSFET switching losses is 0.
I don't think that was the case. Can we go to the table?
No, the body, we said
The body diode
the body
in the
diode
high side is 0.
in case of a low side recirculation.
And the switching losses is 0 in the low side. Yes, I think maybe we can take a circuit or yeah. Yeah, this one can work. So Christoph, when Christoph explained how the waveforms in an half bridge with, let's say, current going out of the switching node, how they work, he said, well, the current has to flow when we turn on off the high side, the current has to keep flowing and it will flow in the body diode. This means that at the time when we turn on the low side, the body diode will be carrying the current, and the voltage at the switching node, which is basically the VDS of the low side, will be minus 0.7, minus 1 volt, depending on how much is the current and what the body diode temperature is. That means that when you turn on the low side, the current has to shift from the body diode to the channel. Once the current has shifted from the body diode to the channel, the low side will fully enhance, but its VDS voltage is already very close to RDS on times the current. So actually the VDS voltage doesn't need to travel from, like in the case of the low side, from 0 to V in. In the case of the low side, the VDS voltage has to travel from minus 0.7 to 0, which is basically nothing. So all the currents that are needed to charge or discharge the capacitances of the low side during the low side switching operations, they are already charged and or discharged. So as a consequence, there is no current needed, or actually no voltage, how do you call it, swept during switching operation of the low side.
With current flowing out.
When the current is flowing out of the switching node. If the current flows inside the switching node, the process is reversed, because it will be the body diode of the high side will be the one carrying the current during the dead times, and the high side will have this advantage, let's call it like this, of not needing to sweep its VDS too much while the current is flowing through the body diode. These operations are called soft switching. So soft switching is when the MOSFET turns on while its body diode is carrying the current, and hard switching, which is the opposite. So when the MOSFET has to start carrying the current from the neighboring MOSFET, let's say. Let's call it like this.
Okay, thanks a lot.
Yeah.
Another question is, did you calculate power losses for each MOSFET, or just one is enough to analyze the reliability?
You need to have both. I would recommend, absolutely. Yeah, because for example, this switching losses topic that is basically associated only to one MOSFET. If the current is completely going out of the switching node, the MOSFET would be the low side, not having switching losses, and the high side has them. What that means, and we can also show it here, the high side has more losses than the low side. So even if you have a 50% duty cycle, and you believe that the losses are equally shared between the high side and the low side, that's not true. And you could, for example, think I measure the losses on the low side, assuming that the high side has the same losses, and you are doing a great misjudgment there. So yeah, I recommend you calculate, you estimate, you measure the losses in both high side and low side.
Thanks a lot. Next
You're
one is
welcome.
in a BLDC motor controlled by FOC mode. Do you know if there are additional points we need to take into consideration in order to estimate the MOSFET's power dissipation?
Yeah. The current that you have to take, since it changes over time, it has to be, you have to take the RMS value, and not the DC value as reference for your calculations. And as I said before, when you do simulations, you have to integrate over an electrical rotation of the motor. Actually, you could do it over, no, over one electrical rotation, yeah, necessarily.
Okay, the next one is in MOSFET switching loss formula, there's a constraint motor assumed to have a very low ripple. If
Yep.
no, sorry, it's the current of the motor, I guess.
The current, yeah.
Yes,
That's correct.
current of the motor assumed to have a very low ripple.
Yep.
If current of motor have high ripple, what is the change in formula?
The change is in the RMS current of that flows in the high side and the low side. Also that one, of course. But as for the losses, yes, the RMS that is considered there will change. Because how did we consider this one being I motor times square root of duty cycle? Well, that formula is gonna change because now that formula comes out of the assumption that the current is constant. You have a square wave current flowing in the MOSFETs. This is not true anymore. You have a trapezoidal, and so you have to find out what is the RMS value of the trapezoidal, which you can find on the internet. You can demonstrate it mathematically. It's a nice exercise, but I don't remember by heart right now.
Okay.
That is one, and yeah, maybe one could assume that the turn on and the turn off losses, instead of considering I motor, one can consider I motor plus half the ripple. But that's really a detail. But if you want to be precise, yeah, you can do that.
But that wasn't quite the purpose here. The purpose was
With very simple calculations.
to be 80-90% right, and
Yes.
this is what it happens.
Yes.
To be under normal application circumstances.
Okay, and we have one last question, which is, are the PCB copper losses so relevant to overall power losses?
We found out at our expenses that is correct. Because you can imagine we did some evaluations and some experiments, and we have shown the results here, and we were struggling to find find out that there was a big discrepancy from what we simulated, what we calculated, even including all the effects possible between the simulations and the reality. And we found out that a lot of losses were happening in the PCB. We saw it through, of course, the thermal camera, and we measured the traces of this on this board. Also, one thing that is not to be underestimated is that if you have a bridge, like a solder bridge or a 0 ohm resistor or a piece of metal that is supposed to, for example, be a loop for current measurement, these also have some resistance, which could be in the order of 1, 2, 3, or even 5 milliohms. So each and every path counts when you sum them up. And you start flowing 8 amps, 10 amps. Well, the formula is I squared R. So 10 amps squared is 100 times 20 milliohm resistance. Well,
Or even 10 or 5.
or even 10 or 5. That gets to a number in the order of the hundreds of milliwatts, or even 1 watt, like in our case.
Yeah.
Okay, one new question came in, and
Yep.
it is how can we estimate power loss in DC link capacitor due to ripple current?
Well, first of all, you have to know your capacitor. So the ESR, and maybe the parallel discharge resistance, but that's a very marginal effect. The main effect is on the ESR, and so they are basically conduction losses. As conduction losses, they can be how do you say,
RMS.
Yeah, they can be calculated as RMS currents, and you have to know what is the waveform or of current that flows in your DC link capacitor. So how much you have filtered before that matters. Or if you can make a very simple assumption that you have the trapezoidal current that flows in the high side minus the DC current component, because current that flows in a capacitor in a PWM cycle has to have a net zero to be in equilibrium, for the system to be in equilibrium. So you can assume that current minus the DC bias is my waveform, and calculate the RMS of that. Again, you can find a lot of formulas if you don't want to make the exercise. I suggest the exercise. I'm a fan of that. Or you can measure it. You can measure it if you have access with a current probe to the DC link cap. If it's big enough, and
But the question is very relevant, because the RMS losses, especially in aluminum capacitor, should not be underestimated.
Yep.
As the cost self-heating in the aluminum capacitor can be quite significant.
Yep.
i.e. The implication on the lifetime and reliability of the capacitor. So very important point.
very good question. Yeah.
Very good question.
Okay, so at the moment, I'm not seeing any further questions.
Yeah.
So as I told you before, the presentation and the link to the on-demand version of the session will be sent out the next days. So you can review the presentation again. I also want to make one comment. So if you're interested more in motor drivers, we also had a webinar last year regarding understanding motor driver thermal management. So you can review our website and have a look at this webinar as well. Please also check our website for future webinars. And yeah, with that, I want to thank you for joining our webinar today, and we are hoping to see you very soon again in one of our webinars.
Thank you.
Thank you.
Thank you. Bye.
Bye-bye.
Bye-bye.